Good afternoon. This is the virtual titration of vinegar lab. I'm Miss Mikesell, and I'm one of the chemistry teachers at Eagle Crest. Our essential question for today's lab is to experimentally determine the molarity of household vinegar using a titration. Then determine your percent air based on the true molarity and whether or not your claim is valid, plus or minus 10% of the true value. If not, we'll need an air analysis where you explain possible sources of air and how those would affect your experimental molarity. And then in part 2, you're going to need to explain why the accepted pH of vinegar doesn't align with the known molarity of vinegar. All right, there are several pre-lab questions that we'd like you to take a moment to answer. I'll read them to you, but if you would pause the video and answer those questions as we move through, that would be great. Let's start by writing the balanced chemical reaction between sodium hydroxide, that's going to be our titrant, and acetic acid or vinegar, HC2H3O2, which will be our analyte, what we're analyzing and determining today. Make sure in your balanced chemical reaction that you identify which is the acid and which is the base, and include states of matter. Just a reminder that water acts as the precipitate in an acid-base neutralization reaction. Then take a second and describe how a titration is done by using the titrant, in this case, our standardized sodium hydroxide solution, with a solution of vinegar where the molarity is unknown. Describe how we'll use phenolphthalein indicator and the titration endpoint. How are they related? How is phenolphthalein indicator and the titration endpoint related? Finally, is there a limiting reactant in a titration, an excess reactant? Explain, please. And then we'd like you to draw a molecular view model for a 3-molar solution of vinegar, a weak acid, and a 3-molar solution of hydrochloric acid, a strong acid. Your model should show the differences in how each acid disassociates in solution. Finally, using your model, let's look at if pH is determined by the concentration of hydrogen ions in solution, which solution would you expect to have a more acidic or lower pH? Explain your reasoning in detail. You should definitely use your drawing to support your answer. All right, let's walk through the procedure for our titration. Step 1 is to obtain a 50 milliliter beaker of vinegar and then use the universal pH probe to test the pH of vinegar. As you can see from the picture, the pH is 2.51. Make sure you record that. Step 2 is to obtain approximately 60 milliliters of a standardized sodium hydroxide solution in your beaker. Record the molarity of that sodium hydroxide as given at the start of the video. This is going to be our titrant, what we're going to use, a solution of known concentration, to do our titration. Then we'll use the funnel to pour approximately 5 milliliters of the sodium hydroxide through the burette to make sure we clean it, drain some through the tip to displace any air bubbles, rinse with 5 milliliters twice more, making sure that we remove any water left over from the last class. And then finally, once your burette is ready, you can fill it with the sodium hydroxide so that the level is somewhere between 0 and 10 milliliters near the top. And make sure we record our exact initial volume of sodium hydroxide using the correct number of significant figures based on the precision of the burette as our tool. And then we're going to rinse a 125 milliliter Erlenmeyer flask with water and pipette 5 milliliters of the vinegar solution into the flask. We'll record the exact volume of vinegar we pipetted into the flask. And we'll add a drop of phenolphthalein indicator to the vinegar. We'll remove the waste beaker from below the burette and replace it with the flask containing the vinegar and indicator, making sure to put a piece of white paper underneath so that we can see when the solution becomes that nice light pink. One person in your group can swirl the flask while another can open and close the stopcock on the burette, to allow the sodium hydroxide to be added to the vinegar. As the end point approaches, use a water bottle to rinse down the sides of the flask, continuing to add sodium hydroxide drop by drop to not overshoot the end point. And once we get to that end point, the persistent light pink indicator color is reached, record the final volume of sodium hydroxide in our burette. Then we're going to repeat the steps again to make sure that we do 3 successful trials. And then finally, we'll drain the sodium hydroxide from our burette and dispose of it down the sink. Rinse the burette with distilled water 3 times, rotating the stopcock. And then we'll place it upside down in the burette clamp to know the next class, to let the next class know that it is ready to be used again. Finally, we'll rinse all of our glassware so that we can clean up the lab. So as you're watching the video today to get your virtual data set, you will need to complete the data table that's on your lab sheet. Make sure for all 3 trials shown in the video, you record not only the starting volume of base from your burette, but the ending volume of base from the burette. You'll need to calculate the volume of base reacted and then the average volume of base reacted. You'll use the average value to do our calculation for the molarity. And finally, you'll need to record the molarity of the sodium hydroxide that they use in the burette. And you'll need to record the volume of vinegar reacted, which, since it's being pipetted into the flask, will be the same volume for all 3 trials. I do want to note that it's very important that you read your burette accurately. Please remember that burettes increase or descend as we go down the burette because they're delivering a substance. So if this is 28, this would be 28.5. This is 29. So take a minute, please, and read what's the volume of the base in the burette from this picture. Hopefully you told me it was 28.89, or you could have a different number right at the end because that is our, you can have a different number at the end of that measurement because that's our uncertain digit, the one that we're estimating. We can clearly see, though, and we should all agree that if this is 28.5, this is 28.6, 28.7, 28.8, that our solution is somewhere between 28.8 and 28.9. And so that uncertain digit, the hundredths place digit, is the one we should be estimating. All right, just a reminder, what you're going to see on the video is that the sodium hydroxide, the base, is going to go in the burette. The vinegar is going to go in the flask along with the indicator. And it is shown in the video, but the base that they're using is a 0.1113 molarity sodium hydroxide solution. And they are going to use for all 3 trials 5 milliliters of our vinegar, the acetic acid solution, of which we don't know the concentration. That's what you're going to be calculating today. As you watch the video, please make sure that you pause. You will have to actually pause the video so that you can take the time to measure the initial and final volumes for each of the 3 trials, and then we'll wrap it up together.
Hi everyone, this video will walk you through the titration of vinegar experiment for Chemistry 10 at Santa Monica College. The video will only show you the experiment. The background and data analysis will be explained by your professor. You will need to record various data points in your lab report as the video goes through the experiment. We start by getting all the necessary chemical reagents and equipment for the experiment. The experiment requires a vinegar solution, a standardized sodium hydroxide solution, and a phenolphthalein indicator. Make sure you record the molarity of the sodium hydroxide in your lab report. We will use 2 measuring instruments, a 50 milliliter burette and a 5 milliliter volumetric pipette. The The pipette is controlled using a pipette bulb that is shown here. We will do the experiment 3 times. The goal is to have multiple data sets so we can check our precision. We start by rinsing the burette over the sink using the ionized water, followed by the standardized sodium hydroxide solution. The goal is to make sure that the inside of the burette contains only sodium hydroxide. We then fill the burette up to the top with the standardized sodium hydroxide solution. Lastly, we flush the tip of the burette to remove the trapped air bubbles. The burette is now ready to use. Make sure you record the initial volume of sodium hydroxide for trial 1. The next step is to rinse the volumetric pipette. We do this by drawing in some deionized water using the bulb. After rinsing with water a couple of times, we repeat the rinsing using the vinegar solution. After the volumetric pipette is rinsed, we draw in exactly 5 milliliter of vinegar solution and transfer it into a 250 milliliter Erlenmeyer flask. After that, we add 20 milliliter of distilled water and 5 drops of the phenolphthalein indicator into the flask. We are now ready to titrate. We start titrating by adding the sodium hydroxide into the Erlenmeyer flask. You can see how the solution turns pink when the sodium hydroxide is added, but then disappears as it is mixed. Our goal is to titrate until the solution is light pink, which corresponds to the equivalence point. We can tell that we are approaching the equivalence point when the pink color takes longer to disappear when we swirl the flask. Here we are nearing the equivalence point, and with 1 more drop of sodium hydroxide, the solution turns pink. We now record the final volume of the sodium hydroxide for trial 1. This is the final color of the titrated solution about 1 minute after the end of the titration. We now repeat the titration 2 more times. Here's the initial volume of the sodium hydroxide for the second trial, and here's the final volume. And lastly, we have the initial volume for trial 3 and its final volume.
Okay, now that you've collected your data, please note that the true molarity of vinegar is 0.83 molarity. So use this theoretical value to calculate your percent error. And if your percent error is greater than 10%, please include an error analysis in your claim. As you think through the error analysis, 2 questions for you to ponder. If you overshoot the endpoint and your solution is too pink, how will it impact your experimental molarity of vinegar that you calculate? Will the percent error be positive or negative? If a bubble of air passes through the burette tip, how would that impact the experimental molarity of vinegar that you calculate? Again, would your percent error be positive or negative? Your last step in this lab is to write your claim. Make sure that your claim answers the essential question completely for the lab. And then the second part of your claim needs to answer the following question. A strong acid with a molarity of 0.83 has a pH of 0.1. Vinegar, which has the same molarity of 0.83, has a much higher pH of 2.4. Explain why the pH of vinegar is higher than the pH of a strong acid, even though the molarity is the same. I hope this was helpful. Have a great night, Raptors. Thanks.